Hi everyone, today we're starting a unit on acids and bases. You'll find that there are acids and bases in food, there are acids and bases throughout your body or throughout the ocean. The concentrations of acids and bases affects the ability of certain things to get destroyed, like in your stomach. There's stomach acid that will destroy certain proteins and hence like sterilize some food. But also you'll see that coral reefs can be kind of destroyed, dissolved by acid in the ocean. One thing about acids that you should know is that they taste sour. So you'll find in lemons, citric acid. We add citric acid to Sour Patch Kids along with tartaric acid. And I guess another thing is bases. They taste bitter. So you'll find some bitter taste in when you're drinking green tea, maybe, or when you're eating some vegetables like broccoli or kale, especially before they're cooked. Acids and bases are present in most living things. The definition we're going to use for acids generally is going to be that of Bronsted-Lowry acids, and those donate H pluses, they give away H pluses, whereas Bronsted-Lowry bases, they accept H pluses. We can use those facts to predict reactions, like between hydrochloric acid and water. All right, so you'll want to memorize this is hydrochloric acid, HCl. And because it's an acid, it will give away H pluses. So what will be left after it reacts with water? All right, so it's going to give away an H plus. So now it'll just have Cl left over. It gave away an H plus. It gave away an H plus. So it was an overall zero charge, but then it gave away a positive charge. So that's going to leave a negative charge on there. All right, and then water. If HCl acted as an acid, the water reacting with it must act as a base. If water acts as a base, it's going to accept H pluses according to the Bronsted-Lowry definition of bases. And so it's now going to have, instead of 2 H's, 3 H's. And as well, having accepted an H plus, it's going to now have a positive charge. It was zero charge and then accepted a positive, so now it's plus 1. So these are the two products that you'll have when hydrochloric acid reacts with water. Let's see, so just H3O plus, that is known as hydronium. You'll want to memorize that. And then Cl minus is also left over. So it turns out that this reaction is not very reversible, but it is ever so slightly reversible. That means that chloride and hydronium can react together to form HCl and water in the ever so small amount. And when that happens, what are these behaving as? Like, is Cl minus behaving as an acid or base when it accepts an H plus from this hydronium to provide HCl? Well, if Cl minus accepts an H plus, it must be a Bronsted-Lowry base. It is acting as a base. But because it's not the base that we had at the beginning, we don't just call it base. It's actually just the twin left over after HCl acted as an acid. It is the conjugate base of HCl. A conjugate base is just kind of the twin left over. What about H3O plus? So if that were to react back into water, it would give away an H plus. Donating an H plus would make it an acid. So hydronium would be a conjugate acid left over after the end of the reaction. You'll sometimes need to identify conjugate acids and bases. You'll know that whatever started as an acid, the thing left over of it after the reaction is the opposite, conjugate base. And whatever started as a base, the thing left over after the reaction is going to be now a conjugate acid. Opposite. Okay. So one way to write out what happens when you dissolve hydrochloric acid in water is this reaction. But this can take longer than a shorter version where we skip writing water. Water is in almost every solution that we prepare, and it is presumably the thing that an acid or base might react with. And so sometimes we skip writing it. So we could just say that in the presence of water, hydrochloric acid just kind of breaks up into chloride and this proton. This is kind of another way of drawing out what happens. This is the shorthand. So H plus doesn't actually exist. This would be super unstable. It would only have a proton, no electrons, so having just positive charge and no negative charge nearby, it would be missing out on that that stabilizing effect of having an opposite charge, according to Coulomb's law. And so this can't really exist except at very high temperatures as a gas, but we write it anyway. So when we write this, we often just mean H3O+. All right. Let's predict another reaction, ammonia. So you're going to want to memorize that this is a base. You'll find it in Windex, to clean your windows at home. You'll also find it in general household ammonia, which can clean other things in your house as well. Note, don't ever react or combine ammonia and bleach. That can create a very dangerous compound. You'll have to evacuate the house. All right, so ammonia is a base. That's a memorized thing. So what is going to be left over after it reacts with water? Well, if ammonia acts as a base, then it's going to accept an H+. So that means that there's now going to be 4 H's on it. And having no charge originally, but accepting an H+, it's now going to have a positive charge. So that means that water must be acting as an acid. It must be giving away an H+. So it had 2 H's before, now it only has 1. And so it's going to just be OH. And then having lost an H+, it's going to have a negative charge left over. All right, so the ammonium is going to end up being the conjugate acid. The thing with the N started with the base, but now it's going to be a conjugate acid, opposite. And the thing with oxygen started as an acid, and now the hydroxide is going to be the conjugate base. Yep, you'll want to know and memorize the name of this thing here. This is hydroxide. Of course, this is also on the list of polyatomic ions. Okay, so we can see that when you dissolve an acid into water, it creates a lot of hydronium. An acidic solution is going to have a lot of hydronium because there's an acid in there. And then if you dissolve a base into water, it will create a lot of hydroxide. A basic solution will have a high concentration of hydroxide. And so one other definition of acids then, instead of Bronsted-Lowry, is the Arrhenius acid definition. So that supposedly will increase the concentration of hydronium or protons in solution. And then an Arrhenius base will increase the concentration of hydroxide in solution. Kind of taking a look back here, we saw that water in the original reaction acted as a base, but then in the later reaction, it acted as an acid. Water can act as either an acid or a base. It's amphoteric. Maybe you know that amphibians kind of live in water and on land. Amph kind of means both. So amphoteric means that something can act as both an acid or a base. So our classic example of that is water. We're going to see in a week or two that what that ends up meaning is water can react with itself, where one water acts as an acid and one acts as a base, and so we end up getting always present in solution, some hydronium and some hydroxide. We'll see that soon. Okay, sometimes you'll need to predict the conjugate acid of something. So what did we do to know the conjugate acid of ammonia? Well, we had ammonia, which was a base, NH3, and its conjugate acid was NH4. It had just one extra H plus on it. So if you ever need to predict what the conjugate acid of something is, you just add an H plus to that thing. So, for example, what is the conjugate acid of hydrogen phosphate, HPO4 2 minus? Well, it's got an extra H plus on it, so it's going to be H2PO4. But then also, it was a 2 minus charge originally, but now we're adding an H plus to it. So it's going to be less negative than before. It's just going to be -1 instead of -2. And then we also might need to predict the conjugate base of something. To do that, just remove the H plus from that thing. So what's the conjugate base of HPO4 2 minus? Well, that's not going to have any more H's on it at all. So it's going to be PO4. And then originally it was 2 minus, but now having lost an H plus, it's going to be even more negative. It's going to be 3 minus. All right, so, and then finally, we've got some just definitions. A monoprotic acid can release only one proton. So, these H pluses, those were protons. H is a proton and an electron, but H plus is positive because it's missing a negative electron, so it's just a proton. We call H plus a proton. So a monoprotic acid can release only one proton. It has just one H on the left. Note that for acetic acid here, which you'll find in vinegar, there are multiple H's, but only one acidic proton, only one that can be released. So that's only a monoprotic acid, the one on the left. And then diprotic acids, those have 2 protons that can be released, like sulfuric acid. And then triprotic acids have 3 protons that can be released, like phosphoric acid. You'll find sulfuric acid in your batteries, in your cars, if you have like a lead acid battery. Or you'll find phosphoric acid added to Coca-Cola to make it more tangy, also dissolving your teeth slightly faster. Okay, and then just kind of finally, neutralization reactions. So earlier we had acids and bases reacting together, but if neither of the things reacting together is water, then you can call it a neutralization reaction. So let's say that you had a bunch of hydrochloric acid solution. It's acidic, but you wanted to neutralize it, make sure it's no longer acidic. So you want to add some base to that acid. And let's predict what happens afterwards. Remember back in like November, we said in double replacement reactions that hydrogens can switch places with metals. So you'll see that here, Na, this metal switches places. So then at the end, you'll get Na plus next to Cl minus. You'll get table salt, and you'll get the H plus now next to OH minus, you'll get water formed. So this is like classic neutralization. An acid, when it reacts with a base in a neutralization reaction, will always form a salt and water. And then now let's predict this next one. Sulfuric acid is neutralized by some potassium hydroxide solution. So switch places between the H and the K. Now you're going to get K plus next to SO4 2 minus. What forms then? You'll need to form something that has a balancing of charge. How many K pluses do I need for this SO4 2 minus? It's crisscross, 2 of them. It's K2SO4. And then we'll also be combining individual H pluses with OH minuses. So crisscross, that's HOH. And then to balance, over here we have 2 H's And only here, over here, we only have one of these H's and one OH. And so put a 2 in front. Now we have 2 H's and 2 OH's. Now here we have 2 H's and only one OH, so put a 2 in front. Now we have 2 OH's. We have 2 K's, we have 2 K's, we have 1 SO4, we have 1 SO4, we're balanced. So again, we react an acid with a base, and that produces a salt and water. Salt isn't necessarily NaCl, that's just table salt, the one that we add to food, but there are other salts. These are ionic compounds formed during neutralization reactions. Thanks for watching.